So, for the last two chapters this semester, we're going to transition from Earth science into astronomy. We're going to learn more about our solar system and the universe beyond. So, for chapter 15, the first of our astronomy chapters, we're going to start off with some brief history of what's gone on in the field since humans first started to realize that we are a planet and exactly how our planet revolves in our solar system, as well as what the other planets are and how they differ or compare to the Earth. So, when we look at ancient astronomy, the first group of people that we really need to study are the Greeks. They used a lot of philosophical debates to try to explain what goes on our planet. So, in these very early days, the Greeks held a geocentric view. This means that at the very center of our universe was the Earth, and that all of the other planets and stars moved around the Earth. At present, we know that this is not true, but before we really got into astronomy, again, we believed in this geocentric universe where the Earth was completely motionless at the very center of the universe, and instead it's every other planet and the stars that were rotating around the Earth. So, to better explain their geocentric model, the Greeks used something called the Ptolemaic system. And this was basically the way that other planets had to rotate and orient themselves around the sun. So, this system helped explain what's called retrograde motion. Retrograde motion is when it appears that in our orbit around the sun that other planets start to move backwards in their orbit. But in reality, these planets are not actually moving backwards. It's because these other planets are orbiting at a different location in our universe than the Earth is. So when this outer planet starts to pass the Earth, it's going to appear like the other planet is moving backwards while staying on the Earth. So, with our early Greeks, they were the first group of people to really try to explain astronomy. And it's not until later on in about the 1600s to the present that we really moved into modern astronomy, where we could truly start to explain what these planets and stars are doing in our universe. So, the first major modern astronomer was Copernicus. He was the first person that decided that the Earth was even a planet. Before him, we didn't realize that we were just one sphere out in our very large solar system. So Copernicus not only concluded that the Earth was a planet at all, he built our first solar centered model. That instead of the Earth being at the center of our solar system, instead it's the sun, and that all of the planets orbit around the sun. Now that we correctly knew that it was the sun in the center of our solar system and not the Earth, this was the major dividing line between ancient and modern or newer astronomy. After Copernicus came this guy called Kepler, and Kepler was the first major modern astronomer. He decided that not only is the Earth a planet, but there are other planets in our solar system as well, and they all revolve around the sun. But what Kepler is most well known for is that the way that our planets orbit the sun, it's not a circular motion. Instead, it's elliptical. It's more like an oval in shape. So that there are going to be times where we rotate around the sun faster throughout the year, and other times when we're farther away, we're going to orbit the sun a little bit slower. And this is all due to the way that physics work. If we are closer to something, we're going to move a little bit faster than if we are farther away. So imagine watching some kind of competitive ice skating. If you're watching and the skater moves in for a really tight, fast spin, they're going to put their arms and they're going to start pulling them closer to their bodies. The closer their arms are to the bodies, they're going to start orbiting or circling more quickly. than they did when their arms were outstretched. So here our planets do the exact same thing as an ice skater would do. Another really famous astronomer was Galileo. Galileo was one of the major proponents that totally supported Copernican, that no, it wasn't the Earth in the center of our solar system, but instead it's the sun. So Galileo is one of the first astronomers that really wanted to collect data from other planets and stars specifically. So he was the first person to ever build a telescope. And even though he did this in the 1600s, and it was kind of basic telescope in comparison to what we have today, he made some major discoveries. He not only discovered that Jupiter was a planet farther out in orbit than the Earth is, but he discovered the four largest moons of that planet. He also was able to start looking at our own moon and looking at different types of features that are located on our moon. And then finally, he was one of the first people to really start studying our own sun, our star that we orbit around. And he noticed the sunspots where we're going to have different colored patches on our sun depending on the temperature of the surface. Another really important astronomer is Isaac Newton. Isaac Newton is most well known for discovering gravity. That basically anything on our planet, if you drop it, it's going to fall to the surface because gravity is constantly pulling things towards the center of the Earth. But Newton not only looked at gravity within our planet, he looked at gravity within the universe as well. And since it's now pretty well known that the sun is in the center of our solar system and that the Earth rotates around the sun, that this law of universal gravitation is going to keep the Earth in that elliptical orbit, that kind of oval orbit, because the gravity from the sun is pulling our planet closer towards it. But we're also moving in a curved pattern. So now we're going to move on to how our solar system started to form according to something called the nebular theory. So, our universe is over 13 billion years old, but the nebular theory is about how our planet started forming, which started about 5 billion years ago. So, our solar system initially started from a solar nebula that condensed into our own solar system. So, in this solar nebula, we have a lot of material just out in space, but it's being collected towards the center as a proto-sun, which literally just means an early sun. But as the sun started to rotate, it formed a disk, kind of like a vinyl record is a flattened disk. And that disk is going to start rotating. So as this disk started rotating out in space, we're going to have some of the material in that disk kind of clumping together. It's going to start colliding with other pieces. And as they start cooling off, they're going to form solids that are called planetesimals. And these planetesimals are basically just very small early planets that might eventually form into a planet. But as these protoplanets, these very early planets started forming, we start to see that based on their chemistry, they're going to develop different layers. So at the very center of these very early protoplanets, we had our denser elements, those metals that are very, very dense and heavy. So they all sank towards the center of these very early planets. But the lighter elements, the ones that have less mass and weigh less, they were not pulled towards the center of these protoplanets, but instead they migrated towards their surfaces. So this allowed these protoplanets to differentiate. They started forming different layers. Their densest layers in the center, kind of like the Earth's core, and then lighter elements that are closer to the surfaces of these planets. So we're going to see later on in this chapter That we have two basic groups of planets within our solar system. We're going to have our closer solid planets, where we're going to see that both Venus and our own planet have atmospheres. We have gases surrounding and protecting our planet. But if we move farther away from the sun, we're going to get into these more gaseous planets that aren't solid like the Earth is, but are mostly made up of different frozen ices, which are called the Jovian planets. So when we look at our solar system, we're going to start at the very center where our sun is located. And then as we move out and towards space, we're going to see different planets and different types of planets forming. So again, at the very center, we have our sun. The first planet away from the sun is called Mercury. Because it's so close to this incredibly hot sun, Mercury does not have an atmosphere. It's literally been baked away from the heat of the sun. But as we move farther from the sun, the next planet we're going to hit is Venus. Venus is going to be a lot more like Earth. It's going to have an atmosphere, but this atmosphere is going to be mostly greenhouse gases, which is going to make Venus incredibly hot, where it averages about 900 degrees every day. One more planet out, we're going to be at our home planet, the Earth. And hopefully at this point in the semester, we've learned some information about the Earth. After the Earth is currently our most studied planet of Mars. So these first four planets, Mercury, Venus, Earth, and Mars, these are our solid planets. Outside of Mars, we're going to start moving into these larger, more gaseous planets, starting with Jupiter, which is a very, very large planet. Then we're going to move on to Saturn, most famous for its rings, then Uranus, followed by Neptune. But one thing I want to point out here is what's called our asteroid belt. That's going to be separating Mars from Jupiter, and the Kuiper belt, which is where Pluto is located. So we see two different groups or types of planets in our solar system. The four innermost planets to the sun are called our terrestrial, or our Earth-like planets. These are Mercury, Venus, Earth, and Mars. And what makes these four planets unique is that they're very small in their size compared to the outer planets, but they're also solid and very dense with very rocky surfaces on them. But if we look at our outer planets, the four larger gaseous planets that are called Jovian planets of Jupiter, Saturn, Uranus, and Neptune, we see that these aren't really solid planets like we would think of the Earth. Instead, they're mostly just gas that is frozen into solids. So we call these very large Jovian planets the gas giants because they're so massive in size and they're made mostly of just frozen gases. Because they're made up of these gases, they have very thick atmospheres that are composed of mostly our lighter elements like hydrogen, helium, and then methane. Whereas here on the Earth, we have a slightly lighter atmosphere, or sorry, a slightly heavier atmosphere of oxygen and nitrogen. So our terrestrial, our innermost planets, again, these are our solid planets where we're going to have a rocky crust, we're going to have a solid mantle, and then we're going to have a metallic core in the middle. With our Jovian or these gaseous planets, we're still going to see a core, but when we were to look at like the mantle area of these planets, it's no longer a solid mantle. Instead, it's going to be liquids and gases that form up these planets. But another major difference are going to be the size of the cores. And these terrestrial planets, our cores make up a substantial amount of our planet. But the cores in these large gas giants are fairly small in comparison to the rest of the planet. So When we look at our solar system, it doesn't matter which planet, which moon we're looking at. One of the things that we commonly see are impact craters, which are going to be these large circular shaped depressions or holes in the surface of the planet where we have small pieces of debris that are coming in and hitting or colliding with the surface of a planet. Even the smallest pieces of debris are going to leave a much larger crater because they're moving at very high velocities or very high speeds, moving through the atmosphere before they collide with our planet. So, even the smallest microscopic pieces of debris are going to be able to help figure the surface of the entire planet over long periods of time. But when we see these very large impact craters that we can see from our own planet on other planets, these are generally going to happen because they're being hit with a really large body, something like an asteroid or a comet. So now we're going to move into our own moon and how it formed. So, compared to the size of the Earth, the moon is actually a very large moon. Most of the other planets in our solar system do have moons, but for the most part, moons are significantly smaller in size than the planet that they orbit, with the exception of our own moon. So, our moon is very, very large in comparison to the Earth. What is also interesting is that the density of the rocks on our moon is almost perfectly matched with the density of the rocks on the Earth. And the moon even has its own core, just like the Earth does, that's made up of iron. But what's different between the Earth and the moon is that the gravity on the moon is about one-sixth of the gravity of the Earth. So you'll notice if you look at videos of astronauts trying to walk on the surface of the moon, they kind of bounce along. But even though it takes them a lot longer to come back down to the surface of the moon, the smaller gravity of the moon is still going to pull those astronauts back down to the surface. And while they're no longer active, the moon used to have plate tectonics that move around very similarly to the way that we have the different types of plate boundaries on our Earth, forming things like earthquakes and volcanic eruptions. But since the moon started forming about 5 million years ago, we've noticed that the moon is constantly being bombarded by very, very small meteorites called micrometeorites. And over long periods of time, this has smoothed down the surface of most of the moon. So imagine using some kind of maybe like a face scrub or a body scrub. You're going to have these small particles inside of it that when you start rubbing it against your skin, it's going to remove some of your dead skin and leave it with a much smoother feel. So these very small meteorites that are hitting the surface of the moon is also going to kind of polish and smooth down the surface. But what we now agree upon is that the moon formed as a result with a planetesimal, another early planet that collided with our Earth before we had a solid crust. So this happened about 4.5 billion years ago. It was so early on that both the Earth and the slightly smaller Mars-sized body that hit the Earth, these two objects that collided were still kind of molten. They were still liquidy. So that when they collided, it threw some of the particles of both that other early planet and the Earth out into space. All of this material that was ejected from these two colliding planets, again, coalesced. It formed a rotating disk around the Earth. And over time, as that disk of debris continued to circle around the Earth, it started coalescing, it started lumping and colliding together until eventually it solidified as our moon. But when we look at the surface of the moon, we're going to see two different types of terrain. One is going to be fairly smooth areas, and the other is going to be very highly cratered. So the first, called the Maria, are going to be these dark regions of our moon. These are going to be lower in elevation, and a lot of these are going to be those craters, just giant craters that formed from asteroids colliding with the moon, as well as when some of those craters would fill in with lava. And that lava is going to smooth out, kind of like a layer of water, and it's going to form these very dark, smooth lowlands called the Marias. But the other type of terrain that we're going to see are called the highlands. Here, these are going to be these much lighter areas of the moon where we can see that there are lots of different craters that have formed. These highland regions make up the majority of the moon. So not only these brighter areas that we can see, but the entire back or the dark side of the moon. So with our surface of the moon, again, these craters are going to be some of the most interesting and most obvious signs of surfaces on our moons. And these happen because of asteroids or meteors hitting the surface and causing not only that depression to form, it's also going to form ejecta. The material on the moon, when it's getting hit by something else, small bits of ejecta, debris is just going to move back out into space. So, on most of the surface of our planet, in addition to just those solid rocks, we're going to see something called lunar regolith. This is basically going to be the soil on top of the moon. So, like we have soil outside, it's just a bunch of very small, unconsolidated debris that we're going to find on the surface of our moon. It's going to be made up of small pieces of igneous rock that formed from cooling of magma or lava. We're going to see glass beads from volcanic eruptions and just very fine, small pieces of dust that have settled on the surface. And just like if we were to walk outside in a big pile of dirt on the Earth, we saw that when the astronauts started walking on the moon, their boots left imprints inside of this lunar regolith or this moon dirt that covers the surface. So now we're going to start moving into our individual planets and what makes them unique. So we're going to start from the sun and work through our innermost planets and then end up with our outermost planets. So the first planet closest to the sun is Mercury, and this is the smallest planet in our solar system. Because it's so close to the sun, it's going to revolve around the sun very quickly. So it takes 1 year or 365 days for the Earth to revolve around the sun. But because Mercury's closer to the sun, it's going to revolve more quickly. And it makes a trip around the sun in about 88 days. But it's going to rotate on its own axis a lot more slowly than the Earth does. So the Earth rotates on its axis once every 24 hours, or our day. But Mercury rotates much more slowly. It takes 176 days for Mercury to see day and night. But an interesting part of Mercury is that it's going to have temperature extremes. It's going to get extremely cold during the night, and it's going to get extremely hot when it's receiving the sunlight during the day. But Mercury is going to resemble our moon in a lot of ways, in that it's not very reflective. It doesn't really have any atmosphere. There are very few gases around Mercury. But we also see a lot of volcanic features, both volcanoes and lava flows that have formed, and a lot of the remains from craters where impacts have happened on Mercury's surface. Our second planet is Venus, And this one's called the veiled planet because until recently we didn't really know what the surface of Venus looked like because it has such a thick and very dense atmosphere. So the orbit of Venus is getting a little bit closer to our 1 year. It takes 225 days for a nearly perfect orbit around the sun. But what's interesting about Venus is that it's the only planet that rotates in the opposite direction of every other planet. Including the Earth, almost every planet rotates in a counterclockwise direction from the sun. But for some reason, Venus is the exact opposite, and it's going to have a clockwise rotation around the sun. But it's, again, just like Mercury, it's going to rotate very slowly on its axis. So that day-night cycle on Venus is 243 days on Earth. But again, probably the most important thing about Venus is its very thick, dense atmosphere. Unlike the Earth that has about 71% nitrogen and 21% oxygen, here on Venus, the most common gas in its atmosphere is carbon dioxide, which is a very important greenhouse gas. Because carbon dioxide makes up almost the entire atmosphere on this planet, we're going to see something called a runaway greenhouse effect. The atmosphere of Venus is able to hold in almost all of the solar radiation coming from the sun. It's going to lead to the surfaces averaging about 450 degrees Celsius or about 900 degrees Fahrenheit because all of the solar radiation coming from the sun is going to get trapped in the atmosphere. But we also see that a lot of this carbon dioxide on Venus is coming from volcanic eruptions. Due to the combination of the thick atmosphere and all of the stuff coming from these volcanic eruptions, the atmosphere on Venus is going to have a cloud layer that's made up of acid rain or sulfuric acid. So it's not a surface that we would want to actually be outside when rain happens. It's not going to be rainwater like we experience on Earth, but it's going to rain very intense acid droplets to the surface of Venus. So we're going to skip the third planet since we've already had 14 chapters so far this semester. Instead, we're going to skip to the fourth planet from the sun, which is Mars. Mars is a lot smaller. It's about half the size of Earth is. But it takes a lot longer for it to revolve around the sun. It takes almost 2 Earth years in order for Mars to make its entire orbit. But we're going to see some major temperature ranges occurring between the equator of Mars and the poles. So we're going to see incredibly cold temperatures of almost negative 150 degrees Celsius at the poles, and then very nice conditions of about 70 degrees Celsius at the equator. So we're currently looking for life on Mars, but it would be very difficult for humans to go live on Mars because there's a very thin atmosphere, at about 1% the amount of atmosphere that the Earth has. And again, this atmosphere isn't mostly nitrogen and oxygen like we have on the Earth. Instead, it's going to be about 95% carbon dioxide, that greenhouse gas, with very small amounts of nitrogen, oxygen, and then gaseous water. So now we're going to move from our terrestrial, those four innermost rocky planets, to our Jovian, those outer planets that are gaseous. So the fifth planet from the sun is Jupiter. And this is the largest planet in our solar system. It is incredibly massive in size. And again, because we're getting farther away from the sun, its orbit's going to get even slower. So it's going to take about 12 Earth years for Jupiter to make one entire orbit around the sun. But it's rotating on its axis very, very quickly. And it takes about 10 hours on the Earth for it to go through a day-night cycle. But when we look at pictures of Jupiter, One of the most obvious things that we're going to see are banded appearances, which we can see here, these kind of orange and white bands on the planet that are parallel to the equator, kind of like the lines of latitude on our planet. And these bands are caused by how quickly this planet rotates. Again, it goes through a day night cycle in less than 10 hours. So it's spinning very, very quickly, which means that the wind in the atmosphere is going to be moving very quickly with it. So we see these bands based on different directions that the wind is moving through the atmosphere. Another pretty obvious thing that you've probably heard about Jupiter before is the Great Red Spot that's found in the southern hemisphere of this planet. And this is just one gigantic rotating cyclone. Think about one gigantic hurricane or tornado, a spinning system of storms just covering a huge proportion of the surface of this planet. Another really cool thing about Jupiter is that it has a ton of moons. We know of 67 right now, but there are probably a lot more moons that are orbiting around Jupiter. But here we're just going to briefly talk about four of them. One of them, Callisto, is the outermost moon. So it's the farthest one away from Jupiter. We also frequently hear about Europa. It's the smallest moon that we've found so far orbiting Jupiter, but its entire surface is an ice. So we think that underneath this ice, there's actually a liquid ocean, which could help us find some kind of living material on Europa. We also see Ganymede, which is the largest moon orbiting Jupiter, and we also see Io. This is the one closest to Jupiter, but it's also the most tectonically and volcanically active bodies, not only moons around Jupiter, but in our entire solar system. Io is the most volcanically active body in our entire solar system. Next up, we have Saturn. All of our Jovian planets have ring systems, but in Saturn, their rings are the most obvious. Again, because we're moving farther away from the sun, the orbit of Saturn around the sun is getting significantly longer, and it takes about 29 Earth years for Saturn to make one orbit around the sun. But it's going to be similar to Jupiter in a lot of ways, in that it has a small atmosphere. It's also going to have the same type of composition of the gases, and it's going to have a small internal structure. But again, the most obvious thing that we see about Saturn is the ring system that orbits the planet. Just like Jupiter, Saturn also has a ton of moons. And here we know 62 of them so far. But we're probably going to discover more moons around this planet in the future. And just like with Jupiter, we're going to see that these moons vary in their size, their shape, what the surface looks like, the age of the moons, and how they were developed. But we're going to focus here on two moons of Saturn. The first is called Titan, and it's the largest moon around Saturn, and in our entire solar system, it's the second largest moon. Titan is so large that it actually has its own atmosphere. It has its own collection of gases around this moon. But another really important moon around Saturn is called Enceladus. And this one is very unique because it still has eruptions of magmas. But instead of having very hot liquid magmas coming out of a volcano, they see something called cryovolcanism. Instead of that hot magma coming out of a volcano, what we're going to have is incredibly cold liquid ice that flows out of the volcano. So instead of catching things on fire like we would see volcanoes on Earth doing, because it's very, very cold liquid ice that's moving, it's going to freeze things on contact. But in addition to the moons on Saturn, it also has this really substantial ring system. And with these rings, we might initially think of them like a disk, just a solid band that's occurring. But instead, each ring is just going to be a collection of really small particles. Anything from water ice, ice that's made up of hydrogen and oxygen, like the ice that we would use in a drink. But we're also going to see very small amounts of just rocks that are orbiting the planet. And it's thought that most of the debris that's forming up the rings of not only Saturn, but our other outermost planets are all going to be happen from collisions from moons, those ejecta. When we have asteroids and meteors hitting the surface of all the moons, that debris is just going to start collecting and forming rings around these outermost planets. But that's just our current thought. It's not definitely decided that this is how these rings formed. It's still an ongoing debate. And then we have our two final Jovian or gaseous planets in our solar system. We have Uranus and Neptune. Elementary age me would have been very disappointed to find out that this planet is actually called Uranus, not Uranus, but Uranus. And probably the most striking feature of Uranus is that it's sideways. When the Earth rotates, it rotates on its axis in this way. But Uranus is sideways. It's going to rotate on its axis going this way in an up and down instead of a side to side motion that we have on every other planet. But it's going to take about 84 Earth years for it to rotate around the sun. And it's going to form the ring systems that we see at Saturn as well. It's just that the rings are smaller and not quite as obvious. And our last planet in our in our solar system is called Neptune. And this is going to be the windiest planet. Because it's so far away from our sun, it takes 165 years for Neptune to make one orbit around the sun. But Neptune has a really interesting atmosphere. It has a lot of gases, but because Neptune is so far away from the sun and moving so quickly, the gases inside of the atmosphere are going to form very intense winds, making Neptune the windiest place in our entire solar system. Because these gases are moving around so quickly, we're also going to see very intense storms developing on Neptune. And you can see that in the great dark spot, this darker blue as well, kind of like we saw the great red spot on Mars. So those are our planets making up our solar system. A little over a decade ago, there was a pretty big debate and scientific decision that we were no longer going to consider Pluto a planet. So now our last planet is Neptune. We call these smaller planets like Pluto dwarf planets now. They're significantly smaller in size compared to the other planets within our solar system. But in addition to these really small dwarf planets, we also see some solar system bodies. These small rocky or ice um, particles that are just moving or orbiting around the sun as well. And these are going to include things like our asteroids, comets, and meteors. So, with our asteroids, these are just leftover planetesimals, those very early forming planets that never actually got large enough to form a planet. So, these are just kind of leftovers from the beginnings of our solar system. But due to the spin of our solar system around the sun, we're going to see that most of the asteroids in our solar system are going to form a belt of asteroids between Mars and Jupiter. This is going to be called our Kuiper belt, and we'll come back to this in a few slides. But these asteroids formed from ejecta. As other objects started impacting our planets and the moons, it's going to cause debris from those planets and moons to kind of break off from the surface and get trapped in this asteroid belt. But asteroids are unique because they have very irregular shapes. We're going to see that our suns and our planets are basically spherical. They're going to be shaped like a ball. But because asteroids are just leftovers from the very beginnings of the formation of our solar system, they have very weird, irregular shapes to them. Another small body that we're going to see within our solar system are called comets. And we'll commonly hear about a comet that might pass by every 50 to 100 years. But comets are basically very dirty snowballs. If you've ever been out after a snowstorm and you look at the roads where a lot of cars have driven, it's kind of like a brown slush. It's going to be a collection of not only the snow that had fallen, it's going to have a lot of dust, some of the ice that's melted back into liquid water, and some frozen gases or liquids inside of it. So, with our comets, we're going to see the nucleus is a very small amount of our comet. But this is where most of those materials are condensed inside of the comet. But as this nucleus starts moving towards the sun, we're going to see a coma develop. We're going to see this bright, glowing head as this comet starts moving towards the sun. As it's moving towards the sun, you can't see it in this picture, but it's going to start forming a tail. It's going to start forming to a peak as it's moving away from the sun. But another small body that we're going to see in our solar system are things called meteors, meteoroids, and meteorites. So the first is called a meteor. This is when we have a solid object that's entering our Earth's atmosphere. But because our planet has a pretty big, thick atmosphere, most of these meteors are going to burn up before they ever reach the surface. So they're just going to be destroyed in the process of moving through our atmosphere. But if that meteor happens to hit the surface of the Earth, we're going to call that a meteorite. It's actually made it all the way through the atmosphere and has collided with our surface. But another thing you might hear from time to time is a meteor shower. So if you check in on the news for the day, they might say, this night or this week is going to have a meteor shower. This just means that a collection of meteors are going to be moving through the atmosphere at the same time. You're going to be able to see maybe one or two meteors per hour burning up as it's making its path through the Earth's atmosphere. And then finally, what we're going to see are dwarf planets. And again, these are just very small planets that are orbiting the sun. Pluto is our most famous example of a dwarf planet. Until about 10 or 15 years ago, Pluto was considered an official planet. But Pluto was significantly smaller than all the other planets, especially those large Jovian planets. Even if we look at Pluto in comparison to a very small Earth, Pluto is about a fifth of the size of our own planet, which is much smaller than those outer planets to begin with. So scientists determined, were kind of decided on calling these very small planets that don't really fit in with those other Jovian planets. They were going to call them dwarf planets. So they demoted Pluto from a planet to a dwarf planet because they discovered two other objects that were basically Pluto in size, called Eris and Ceres. So these were basically Pluto-sized planets in our outer atmosphere. But because they're starting to discover more of these smaller planets, they don't want to call them planets anymore. So they're called dwarf planets. They're planets in every aspect. Some of them even have their own moons, but they're significantly smaller than all of the other planets within our solar system.